Hello, welcome to the video of our paper on solving asymmetric diagonally dominant linear systems in sublinear time at ITCS 2026. I am Mingji from Renmin University of China, and this is a joint work with Professor Kwok from Shanghai University of Finance and Economics and Professor Wei from Renmin University of China. So let me start with some backgrounds. As you know, solving systems of linear equations in the form of mx equals b is a fundamental problem in both computer science and mathematics. And in the past decades, the solvers for many special classes of systems have been extensively studied and developed. Among them, a breakthrough result is nearly linear time solvers for Laplacian systems and more generally for symmetric diagonally dominant or SDD systems, which is developed by Spellman and Chen in 2004 and had led to the influential Laplacian paradigm. So let me say a bit more about the Laplacian and SDD systems. The Laplacian systems are associated with undirected graphs. So given a graph, we can define its graph Laplacian matrix denoted by L sub g, which equals its diagonal degree matrix minus the adjacency matrix of the graph. So for example, for the graph on the left, its Laplacian matrix is its 4x4 matrix on the left, with its diagonal entries representing the degrees of each node, and the off-diagonal entries are -1, whose positions corresponds to the existence of these edges on the graph. And we just call this whole linear system a Laplacian system. And we can also consider the more general SDD systems. In an SDD matrix, the off-diagonal entries can be quite arbitrary, and we only require the symmetry of the matrix and the diagonal dominance property in the sense that each diagonal entry is larger than or equal to the sum of the absolute values of these off-diagonal entries in each row. So as the story goes on, in 2016 and 2018, the Laplacian solvers had been further generalized to nearly linear time row or column diagonally dominant solvers, that is for RDD or CDD systems. So naturally, for an RDD system, we do not require symmetry anymore, and we only require diagonal dominance for each row. And of course, the CDD systems are defined in the natural column-wise way. And for the subject of sublinear time solvers, a work by Andoni, Cross-Gamma, and Pogro at ITCS 2019 pioneered the study of algorithms for solving a single entry of some well-conditioned SDD systems in sublinear time. So given this previous work for RDD and CDD solvers and sublinear time SDD solvers, it is quite natural to ask the question that can we also solve RDD and CDD systems in sublinear time? And in this work, we give a positive answer to this question for some well-structured RDD or CDD systems. Of course, we need to first properly characterize what it means by well-structured for RDD and CDD systems here. So to formally define our problem, we are considering an underlying RDD or CDD system mx equals b, where the matrix M is a square matrix and B is a vector that lies in the range of M. And our algorithms are given standard oracle access into M, B, and an extra target vector T. And our goal is to compute an approximation of the inner product between the target vector T and a solution X star. So here the X star is a particular solution to the system mx equals b. So we are actually not requiring the matrix M to be invertible, and we will specify what is the particular solution X star that we are going to consider. As the examples, we will see that the problems of computing personalized PageRank and effective resistance between two nodes on the graph can be formulated as special cases of our framework. So in this talk, instead of showing you the technical results, I'm going to show our main contributions at a higher level. Our first contribution is a generalization of the formulation and results in the previous ITCS paper from SDD systems to RDD or CDD systems. And we do so by generalizing the key quantity, the spatial gap, to a novel concept called maximum p-known gap that we propose. And secondly, we derive more complexity upper bounds for solving these RDD or CDD systems. And we do so by adapting some widely used techniques for local graph algorithms, namely random walk sampling, local push, and the bidirectional method, which combines the previous two algorithms. Okay, next I will show you some main ideas of our work. First, we need a mathematical characterization of the particular solution X star that we are going to consider. So we express it via a power series expansion. To this end, we first decompose the matrix M as M equals dm sub am, with dm being the diagonal part of the matrix M and am containing the negative or the off-diagonal entries of M. So for some certain types of M, we will have the following simple formula for the solution X. For the equation Mx equals B, we just multiply by the matrix D inverse on the left for both sides, which yields I minus D inverse A times X equals D inverse B. And if M has some nice properties, we can express the inverse of this I minus D inverse A by a power series involving the matrix D inverse A, just like the geometric series for real numbers. So the problem is that for a general RDD or CDDM, this power series does not always converge. So to guarantee convergence for a general RDD or CDDM, we define the particular solution X star as follows with a slight modification. We just replace the matrix D inverse A by its average with the identity matrix and also multiply by 1/2 on the left. So with this formulation, we are able to prove that the X star is actually well defined and indeed is a solution to the equation Mx equals B. And also for the special case where M is a symmetric diagonally dominant, the solution X star has a closed form expression involving a more parallel pseudo-inverse, and this exactly matches the particular solution considered in the previous work. So as the expression of this X star involves an infinite sum, for algorithmic purposes, we will need to truncate this infinite sum to some level L, where L is a truncation parameter to be determined later by our algorithms. So we will approximate the solution X star by its truncated version denoted by X star sub L, which simply truncates the infinite sum to the first L levels. So our next step would be to upper bound the truncation error introduced by this in terms of some quantity of the matrix M. And here is where the notion of p-known gaps comes in. By looking at the expression for X star, we'll notice that intuitively a stronger diagonal dominance property of M would imply faster convergence for this infinite power series, because larger diagonal entries would cause the matrix D inverse to be smaller, and so the power would be smaller for a fairly large exponent L. To quantify this intuition, we can consider the following quantity for the RDD case, that is 1 minus the induced infinity norm of D inverse A, which equals the minimum over all the rows J, and the inside value measures how much the diagonal entry in the Jth row dominates the sum of other entries in that row. This quantity is always non-negative, and the larger this quantity is, the stronger the diagonal dominance property of M possesses, and also the faster the convergence will be. On the other hand, for the CDD case, the corresponding quantity would be 1 minus the induced 1 known of A multiplied by D inverse on the right. So this hints us to consider the general quantity involving a general P, which is 1 minus the induced P known of the matrix AM multiplied by D to the minus 1 over Q on the left, and multiplied by D to the minus 1 over P on the right. Here, as usual, Q is the associated quantity with P that satisfies 1 over P plus 1 over Q equals 1. So again, there is a problem with this definition, because this definition can be 0, which makes it useless as a notion of structural gap. To remedy this, we define the p-known gaps with a slight modification of this quantity we just saw. We denote the p-known gap as gamma sub p on, and we replace the matrix we just saw by its average with the identity matrix. And also, we only consider the induced p-known of this linear map restricted to this relevant subspace. And furthermore, we define the maximum p-known gap on as the maximum of this value taken over all possible p. This is because we are going to show that we are able to bound the truncation error as long as the p-known gap is large for some p. So we have the following theorem. As long as M is RDD or CDD, then its maximum p-known gap will be strictly positive and also at most 1. So this makes it a reasonable notion as a gap. And furthermore, if M is symmetric, the maximum p-known gap is achieved with p equals 2, and this also equals its spatial gap, which is a well-studied quantity of M, defined as the smallest non-zero eigenvalue of the normalization of the matrix M. So with this notion of maximum p-known gap, we are able to upper bound the truncation error on the infinite power series. Suppose that we have a parameter gamma as a lower bound of the maximum p-known gap of M. To ensure that the truncation error is upper bounded by some parameter epsilon, it suffices to set the truncation parameter L to be of order 1 over gamma, with only polylogarithmic dependence on some other quantities such as 1 over epsilon. So I would like to clarify that our formulation so far exactly reduces to that considered in the previous ITCS paper when M is SDD. So our formulation is strictly a generalization of theirs. Okay, now let me introduce two special cases of solving RDD or CDD systems, that is, computing PageRank and effective resistance on graphs. So speaking of PageRank, it is Google's celebrated algorithm originally proposed for ranking the websites according to their importance. And mathematically, the personalized PageRank vector with respect to a decay factor alpha and the source probability distribution S is defined as follows. It is a stationary distribution that satisfies the personalized PageRank vector equals alpha times the source distribution plus 1 minus alpha times the random walk matrix times the PageRank vector itself. So here the degree matrix is a diagonal out degree matrix. And equivalently, we can write this definition as the following equation, where the involved matrix here is the degree matrix minus 1 minus alpha times the adjacent matrix transpose. So this involved matrix is strictly column diagonally dominant, and thus it is invertible. And also for undirected graphs, the matrix is symmetric diagonally dominant. And we can check that for this matrix, the decay factor alpha serves as a natural lower bound for its maximum p-known gap, up to a constant of 1/2. On the other hand, in the context of effective resistance, we only consider connected undirected graphs. And we view the graph as an electrical network where each edge has a resistance 1 over its weight. So the effective resistance between two nodes S and T is defined as the amount of equivalent resistance between them if we suppress the rest of the graph into a single resistor. And for our purposes, we can consider the algebraic property of effective resistance. That is, the resistance between S and T equals the projected form of the pseudo-inverse of the Laplacian matrix with respect to the difference of two unit vectors ES and AT. So in our framework, when we set the matrix M to be the Laplacian, and we set the vectors B and T to be both ES minus ET, And this will lead to that the amount T transpose X star that our algorithms are going to approximate exactly equals the effective resistance between S and T. So naturally, this matrix M is SDD because it is Laplacian. And also its maximum Pinon gap exactly equals the spectral gap of the Laplacian. Okay, next I'll briefly introduce some ideas of our algorithms for solving RDD or CDD systems. Our first technique is random walk sampling, which is in fact a traditional technique. So recall that now we aim to estimate the inner product between T and the truncated version of this power series. And the key observation is that when M is row diagonally dominant, the relevant matrix half I plus D inverse A taken as entry-wise absolute values is row substochastic, which makes it a transition matrix for random walks on the graph. So with this interpretation, we can estimate the whole quantity by sampling random walks of lengths between 0 and L minus 1. And these random walks start from the normalized version of the vector T as a source distribution and transitions with this row substochastic matrix. By recording the quantities related to these sampled random walks, we are able to obtain an unbiased estimate for this whole quantity. So by using a simple Hofstee bound argument, we can prove the following theorem. Suppose that M is RDD and we are given a lower bound on its maximum Pinon gap. And also suppose that we can simulate one step of the aforementioned random walk in constant time. Then our randomized algorithm can compute an estimate for the inner product between T and X star within an absolute error bound involving the infinity norm of D inverse B in time inversely proportional to gamma cubed and epsilon squared. So this result generalizes the algorithmic result in the previous work for SDD systems to RDD systems. And in fact, the previous work proves that in this result, a quadratic dependence on the structural quantity is necessary. And we further prove that a linear dependence on the error parameter is also necessary. So these are in contrast with the global nearly linear time solvers. And while the result on the previous slide is for RDD systems, for CDD systems, we can derive similar results by the following observation. We can check that for the expression for this target value, if we swap the rows of B and T and also replace the matrix A by its transpose, the expression remains equivalent. So if M is CDD, instead we can consider the matrix involving the inverse A transpose, which is again row substochastic. So we can apply the previous algorithm, but this time we sample random walks from the source distribution B. So in general, our results for RDD systems can all be adapted to CDD cases by just swapping the rows of B and T. Our second technique is the local push method, which is motivated by the forward push method for computing page rank from a single node. So forward push algorithms maintain two quantities, the reserve and the residue for each node on the graph, and it relies on the key push operation. In each push operation, we convert an alpha fraction of the residue for a node to its reserve, and also propagate the rest of the residue to its outer neighbors. So the forward push algorithm iteratively performs these push operations until all the residues are sufficiently small. As it turns out, when the algorithm terminates, the reserves will serve as the estimate for the page rank vector from the source node S, and the remaining residues will capture the approximation error through an invariant equation that is preserved by the push operations. So motivated by this, we can formulate an algebraic push primitive for RDD or CDD systems. So we maintain different levels of residue and reserve vectors, and we initialize the residue at the zeroth level to D inverse B. And as long as there is some residue whose absolute value is larger than a given threshold Rmax, we perform a push operation as follows. We convert the residue to its reserve, and we update the residue on the next level by applying the transition I plus d inverse A divided by 2 to this residue on this entry. So this can be understood as approximating this quantity starting from the vector d inverse B on the right and iteratively performs the red transition matrix as long as there is some large entry in the residue. And interestingly, the push primitive will exhibit different properties for RDD or CDD systems. Specifically, for RDD systems, push admits a closed form accuracy guarantee, and for CDD systems, it admits closed form complexity bound. So combined, for RCDD systems, it will admit both the accuracy and complexity bounds. But here we are not going to show you the details. And finally, there is the bidirectional method. The bidirectional method is actually once again motivated by algorithms for estimating page rank. Originally, it was the bi-PPR algorithm for computing the single pair personalized page rank value from the source node S to the target node T. In this bi-PPR algorithm, we first perform backward push from the target node T, which is actually a different application of the push primitive. And secondly, we perform random walks from the source node S to detect the subgraph explored by the backward push process. So under our framework, we can consider using the bidirectional method to approximate this target value. After performing the push primitive from the right-hand side vector d inverse B, we can have the following relationship promised by the invariant property of push. So here's the difference between the target value and the value we can obtain from the push process equals the following somewhat convoluted expression. But this expression is in the form of the original expression that we aim to approximate, with the right-hand side d inverse B replaced by the sum of the residues obtained by the push algorithm. So when M is RDD, then we can perform our random walk sampling algorithm to estimate this difference by sampling random walks from T. So combined, our method is first perform push from the right-hand side d inverse B, and then use random walk sampling from T to estimate this difference. And we will use some parameter balancing strategy to obtain a good complexity bound. And again, I'm omitting some details here. Okay, finally, let me conclude this presentation. In summary, we have shown that well-structured RDD or CDD systems can be solved in sublinear time. Here, well-structured is measured in terms of the novel quantity of maximum P-norm gap that we propose. And this framework also provides a unified and more general way to understanding the study of sublinear STD solvers and also some local graph algorithms. In this direction, there are still some open problems. So the first one is, of course, try to bridge the gaps between the known upper and lower complexity bounds for solving these systems. And the challenge is that the complexity bounds may contain many quantities depending on both the system and the error measures. And the second, both interesting and important problem is try to relate the P-norm gaps to the combinatorial properties of the systems, since they are the generalizations of the spectral gap. And finally, we can try to find more applications of these sublinear RDD or CDD solvers beyond the problems of computing PageRank and effective resistance on graphs. So thank you for watching this video.